Can those pairs of electrons get any farther apart than they are? No, they stay as repelled as they can be, 180. It cannot get any farther apart than 180. You have learned how to draw Lewis structures. Now we're going to use that to determine the actual three-dimensional shape of molecules. So what you need to learn is VSEPR, and this is just an acronym that represents this theory. So the letters stand for valence shell electron pair repulsion, and that is really the theory that describes the shape of these molecules. So electrons are negative, right? And pairs of electrons are going to repel each other as far apart as possible. And so that is the theory behind the shapes of molecules. So how do you do this? Well, these are the steps you might want to write down. First of all, draw the Lewis structure. And you know what? We can all use more practice in drawing Lewis structures. So draw the structure, and then you're going to count the domains. And that would be, let me just draw a molecule for you here. So let's just say we were doing water, and we had 2 bonds. So the central atom would be oxygen, and then the total domains around the central atom, there's 1, 2, 3, and there would be 4 domains. Okay, and then that would determine the electron geometry. I'm going to show you a chart in just a second. And then the lone pairs, there would be 2 lone pairs. And we would go to this chart and determine the shape of the molecule. And there's the chart. So this one that we just did was 4 domains, and then, and then 2 lone pairs, so that would be bent. So this little chart you need to more or less memorize, and I'm going to give you an example of each shape and show you how simple this can be. So there's the steps, and there is the table. Now, these are a couple molecules. I actually have them built. This is carbon dioxide. The black is carbon, and then we have 2 oxygens. Notice it's double bonded together, and you can actually see the shape right now. So let's count the domains. There's 1 domain, 2 domains. So I have 2 domains, no lone pairs. And so if I go to the chart, 2 domains, no lone pairs, that is linear. So we will label this as linear. And the angle between those bonds is 180. It cannot get any farther apart than 180. All right, the next one is BF3, and before you say this out loud, you're right. This is an exception to the octet rule, and you know what? All stable compounds don't necessarily follow the octet rule, and this one is actually stable. So we've got, let's count the domains. There's 1, 2, 3 domains, and there are no lone pairs. So I'm going to go over to the table, 3 domains, no lone pairs. Both the electron and the molecular geometry is called trigonal planar, and that angle is 120. So this is trigonal planar, and I'll show you a model of that. This little molecule right here, trigonal, meaning 3, and that angle there is 120. I'll draw that for you, 120 degrees. Okay, and then planar meaning flat. All right, trigonal planar. So let's go on to the next one. This is methane. Methane has 4 domains, 1, 2, 3, 4, no lone pairs. So let's go to the table. We have 4 domains, no lone pairs. It is tetrahedral in both electron and molecular geometry. And here is a molecule of methane. Now, this is a perfect example of VSEPR. Can those pairs of electrons get any farther apart than they are? No, they stay as repelled as they can be. And so this is what we call tetrahedral. And that bond angle there is 109. Okay, tetrahedral. All right, what would happen if we had 4 domains, but we were missing an atom on one? And that would look something like this. Okay, and this is ammonia. So I've got 1, 2, 3, 4 domains, and there's 1 lone pair. And we go to our table. There's 4 domains, 1 lone pair. So this one is called pyramidal. So ammonia is pyramidal. and it kind of looks like a pyramid there. So why are these bonds pushed down a little bit? Notice it's not planar. Well, actually that lone pair on the top there, which can be represented by this, I'll draw a little region there. Lone pairs are actually a little bit larger than these shared pairs, and it's gonna push those bonds down just a little bit. And so that angle is gonna drop down to about 107, okay, instead of 109. Now, what if we were missing one more atom on a tetrahedral structure? Here's one with 4 lone pairs. 4 electron domains and 2 lone pairs. So this is the one we did at the very beginning. 4 domains, 2 lone pairs, and that is bent. My bond angle is 105. And so you can see why, because we have 2 lone pairs pushing that shared pair down just a little bit more. So water is bent. Now, the shape of molecules is very important in determining intermolecular forces and how these things interact with other substances and actually eventually reactions. So it's going to take a little bit of practice to draw the structure, use the chart, count up your electron domains, count your lone pairs, and then choose the shape. Now, are there more shapes than this? There are, and there's probably a big table in your book. There's some quite a few shapes that I don't know how many you need to memorize, but I think this is a really good start. If you can memorize that section of the table, you'll be in good shape.